I'm now going to look at another application of geometric series. In this case, we're looking at annuities. Annuities are situations where a fixed amount is consistently being placed in an investment or in a bank to accumulate. So, for example, it could be putting $100 in a bank account at the beginning of every month, or $1,000 on the birthday of a child for every year until they turn 18. So the same amount is going into an investment or in a savings account, and it's accumulating compound interest. And we want to know how much money there is at the end of that time period. A really good example of that is superannuation. Superannuation works over a very long period of time, from the time you start working till retirement, and wages don't stay fixed, and also rate of return doesn't stay fixed. But for us to be able to get an understanding of how these work, we simplified the problem somewhat. So here I have an example, and I've tried to keep it as realistic as possible, and I'll go through it as we read through the example. So in Australia, the compulsory rate of superannuation contribution, that should say, is 9.5% of an individual's gross salary. So what that means is, for example, in this example, Maya is a teacher earning a salary of $85,000. So the employer must pay on top of the $85,000 9.5% into a superannuation fund that Maya has no access to. So it's part of her salary, but she doesn't access it. It goes into a superannuation fund on a monthly basis as she gets paid, and it accumulates over her career, so that when she retires, she has a lump sum that she can use to support her retirement period. So I've picked a teacher's salary because teachers' wages don't change much from month to month, to try to make it more realistic. So first part is calculate Maya's monthly super contribution. So let's highlight what we have. The contribution from the employer is 9.5% of her salary, and we want to know how much that actually is per month. Then it goes on to say Maya works for 35 years with little change to her income over this time, because we need that 85,000 to be constant, or the monthly installments to be constant, so we can do a calculation. Her super returns 6% per annum for the duration of her career. How much will she have in her super at the end of her career? So at the end of 35 years, how much money will there be? And then last part, if she needs $1 million to retire on, then how much does she need to contribute on top of her monthly contribution from her employer? So employer will give 9.5%. Well, let's see if that's enough to make her $1 million. If it's not, then we have to work out how much extra she needs to contribute. Okay, let's go back to part A. Actually, let's do a quick summary. Contribution from employer is 9.5%. And again, we work in decimals, not percentages, so 0.095. And her salary is $85,000. Now in part A, they want the contribution in dollars terms. So that would be 0.095 of 85,000. which is $8,075. Now that's per annum, but payments are made, wages are paid monthly, so we need to convert this to monthly. That divided by 12 is $672.92 per month. Okay, so we know how much is being paid into her account, into her super account on a monthly basis. We had a sentence question, calculate Maya's monthly super contribution. So let's write, therefore, okay. Part B. This is where the guts of this question is. Part B says, she works for 35 years. The return is 6% per annum. How much money will there be at the end of her career? So, N is 35 years, but we need to convert to monthly because payments are made monthly. So that's 420 months. The rate was 6% per annum, which is 0.06, but we need to divide that by 12. So that's 0.005 per month. And then we have the amount being invested on a monthly basis. I'm going to draw a timeline to assist with our calculation. This is time 0. This is the first day Maya starts working. She does not get her first pay until the end of the month. So this is month 1 finished. Her first payment is made here. Now, that's the end of month 1. She will go to 420 months. How long is this payment going to be sitting in her super fund? We need to work that out. Then at the end of month 2, she will get another super payment. This payment sits in the account for 1 less month because it's gone in at the end of month 2. Month 3, another payment. Month 4, another payment, and so on. The last payment, month 419, accumulates interest for 1 month. Well, that would be the second last payment, and the last payment accumulates no interest at all. So the first amount that we calculate would be this first P, that was $672.92. We're applying the compound interest formula because it's accumulating interest compounded monthly, so that would be 1.005, and it's in there for 1, 2, 3. You can see 3 months at 4, so by 420, that would be 419 payments. Amount 2, that's this one here, that's an amount of $672.92, accumulates interest at 0.005, and it's in the account for 418 months. Amount 3, 672.92, 1.005, 417, and so on. And I hope you can see we've established the pattern. The last amount Now that's amount 1, amount 2, amount 3, amount 4, so that would be amount 420 will be $672.92, and that does not accumulate any interest. So I could really write this down if I wanted to as 1.005 to the power of 0, because there are 0 months, or I can just leave it out, and I'm going to do that. I'm going to leave that out. So how much will Maya have at the end of this time period? Well, the total will be amount 1 plus amount 2 plus all the way to amount 420. So if I write that out, every single one of those terms has $672.92. So I can take that out as a factor straight away. And then I have 1.005 to 419, 418, and so on. 1.005 is the second last term, and 1 is the last term, which comes from this A420. If I take $672.92 out as a factor, I've just got 1. So this is what we write now. We have established a pattern, and we know this is a geometric series. I am going to look at my series going this way. So my first term is going to be 1. My ratio is going to be 1.005. And my number of terms, that is 490. But remember, we start with to the power of 0. So that's 420 terms. Using the sum of geometric series, we have $672.92 times A, which is 1, times R, which is 1.005 to the power of n, minus 1 all over 1.005 minus 1, which is 0.005, which gives me $958,716.05 to the nearest cent. So again, the question was in words. So go back to the question. How much will she have from her super investment at the end of her career? So we'll finish with the sentence answer. Therefore, okay, so the last part requires us to see how much she needs to contribute on top of her employers, so that she's have $1 million in there. So our value is pretty close to $1 million anyway. To do this last calculation, we're going to use the formula we established in part B. So in part B, we had the total equaling the amount 672, but now I don't know how much that is because I'm looking for $1 million, but everything else has stayed the same, so that would be 1.005 to the power of 420 minus 1 over 0.005, and I want the total to be 1 million. So my amount is going to be 1 million divided by 1.005 to the power of 420 minus 1 over 0.005. Let's work that out. That gives me $701.90. So that's how much she needs to invest. Since her employer is paying 672, Maya's contribution is given by $701.90 minus $672.92, which is $28.98 to the nearest cent. Okay, so generally the questions do not have part A and part C. It's usually around that middle part B. How are marks distributed? There is a mark assigned for ability to establish a pattern. There is a mark usually for the statement of geometric series and the sum formula, and then there is a mark for the final calculation. So one mark there, one mark for establishing geometric series, and one mark for the final answer.